check out this this snazzy I feel like I'm doing some poetry. I'm gonna read from you from this high stool. But how fun is this? I saw it in the corner. Thought I'd try it out. Sit and see. It's the best of both worlds. We left off still in 2.3, but just wrapping up 2.3, where we found the intersection of two lines, right? And then we'll dig into, oh, sorry, not 2.3. That's the one that I let you do on your own, but really it's just more practice problems, right? Word problems that you can solve. And I posted the solutions to those practice problems as well on Moodle. And so give it a go. Let's see what it looks like on here. Where is it? Okay, well, there's a lot of hidden stuff here. A lot of hidden stuff. 2.3, you're doing on your own. I should make that a bonus assignment, shouldn't I? Just 2.3. Sure. Why not? That might be nice of me. But it is stuff that I want you to know and try, and so but I can be nice. I can be nice. Oh, that's what I wanted to ask you guys. Did you have time to talk about whether you want to keep test 1 on Tuesday?
Yep, Tuesday.
Tuesday's good. Just a nice, calm way to come back from Thanksgiving.
Our chemistry, that will be Thursday.
Oh, so that's perfect. Yeah, then we'll keep it as is, all good. I'll make a note here. Test number 1 on Tuesday. Oops, that doesn't look like Tuesday, but it is there.
Maybe all in chapter 1.
1 and 2. Yeah. Yeah, and I'll post a practice test. And you'll have those chapter 1 practice problems. They're just for practice. Chapter 2 practice problems. Right, so lots of practice available. And the practice test will give you an idea of kind of what types of questions and the length, of course. Okie dokie. 2.2 was the intersection of two lines of f of x and some g of x. Right? How do we solve for the intersection? Well, the intersection is where they both have the same xy coordinate, right? And so if f of x is a y and g of x is a y, then y equals y, right? I set those equal to each other, and then I can solve for the x that makes that happen. I'll bump this down just a smidge here, right? We set f of x equal to g of x and solve for x. Solve for x, then solve for y. Solve for y, which is equal to f of x or g of x. I should say and. Okay. So that's where we left off last day, and then we kept this for when you're fresh, which is today, believe it or not. We can find this intersection. Right? We've got two lines. F of x is 3x plus 1, and g of x is -2 minus 1 over 3x. Here we go. Oh, first, any questions before we do this example? Okay. So if we let f of x be g of x, right, that's at the intersection by definition. Oh, and I just remembered because I made a recording this morning and I had to disconnect my audio, but it looks like it's all good. So hopefully I'm not on mute. I'll find out. Looks okay though. Okay. F of x, we can replace it with 3x plus 1. And g of x, we can replace it with -2 minus 1 over 3 times x. Oh. Notice that all I have left are x's, right? And some constants. And so I can collect like terms. And I'm going to pull all my x's to the left-hand side and all my non-x's to the right-hand side, kind of in a group move. So that leaves me with 3x plus 1 over 3x is -2 minus 1, right? Kind of synchronized math, I guess. You can try it on your calculator, right? For your collecting your x's, you do have a 3 and a 1 over 3x, right? And so technically what you're doing is you're pulling out a common x and you're adding 3 and 1 over 3. Well, technically, that's what you're doing. And so, and maybe I should write this 1 over 3 properly. You'll see why in a second. If you try this on your calculator, let's see what it looks like. Making sure you wrap up your 1 over 3. Otherwise, it might do 3 plus 1 and then divided by 3. And so you want to treat the 1 over 3 as a fraction. So do 3 plus bracket 1 over 3. It gives me 10 over 3, which is just 3.33333, which makes sense. Right? You're allowed to use your calculator. Right? So if the fractions, if you don't like them, that's okay. But how would you add these fractions? Uh-oh, losing my voice already. That's what I get for doing that. I didn't have time to finish a practice test in class last night, so I said, oh, I'll make a recording, but then I had to make it. Thanks. If I want common denominator, right, which is what I need to add or subtract fractions, so I need a common denominator of 3, then what can I do? I can use this trick where I multiply by 1, right? 3 over 3 is 1. Multiplying by 1 doesn't change anything, right? And so I'm allowed to multiply 3 by 3 over 3, right, to alter it into something that's over 3. So then I get 9 over 3, which of course we know is 3, right? And so all I'm doing is I'm replacing this with 9 over 3 plus 1 over 3. -2 minus 1 puts me at -3. How do I add and subtract fractions, right? Once I have that common denominator of 3 here, right, then I add or subtract the numerator, right? 9 plus 1, which is what puts me at 10 over 3. But like I said, if you just go from basically here, 3 plus 1 over 3 on your calculator, you would get 10 over 3, right? But the reason is this. And so we get 10 over 3. And then when I'm done kind of collecting like terms, I like to move my x to the right-hand side. X times 10 over 3 is still true, but just looks nicer if it's on the right-hand side. And I know I can't explain it. If I'm pulling out a common factor of x, then I like to pull it to the left. And then when I'm done with it, then I scoot it back to the right. Can't explain it. Just is. How do I solve for x here? Well, I'll make a note here, right? You are allowed to use your calculator. But it's nice to have a kind of a safety net, right? You can practice your fractions and then check with your calculator. Right? That's nice. So now, solving for x, I have to multiply both sides by 3 and then divide by 10, right? Which is really just dividing by 10 over 3, right? But you can do it incrementally if you want to. So you get x must be negative 3 times 3 divided by 10. If you want to think of negative 3 as a fraction, what would it look like? Negative 3 over 1 divided by 10 over 3, but you have to flip and multiply, right? And again, as long as you put fractions around the 10 over 3, you're allowed to use your calculator, right? Otherwise, it'll do something weird, I think. I fear. Negative 3 times 3 makes negative 9 over 10. Negative 9 over 10. Does it make, or negative 0.9? If x is negative 0.9, let's add a page here. We can solve for y, right? The intersection is a point, right? An xy point. One of the things that I encourage you to do is if these two f of x and g of x have to be the same at this point of x, then a nice way to be able to check your work is evaluate f of x as well as g of x and just make sure you get to the same value, right? So we'll start with f of x is 3x plus 1. And then I'll do g of x, which was something weird, negative 2 minus 1 over 3x. And if you get a nice decimal, you're welcome to just use the decimal. Might be a little bit cleaner to look at. And so f at negative 0.9 is 3 times negative 0.9 plus 1. Negative 0.9 times 3 plus 1. I get negative 1.7 is f at negative 0.9. So what I'm hoping is that I find negative 1.7 on the g of x as well, right? Otherwise it won't be the intersection. G of negative 0.9 is negative 2 minus 1 over 3 times negative 0.9. I'll do 1 over 3 times negative 0.9 and then negative 2 minus that. Phew! G of negative 0.9 is negative 1.7. Oh, that's a relief. Make sure they are the same. It says sure. Which they are. And can use Desmos. Oh, it keeps doing this weird thing where I have to restart it. There. Was it 3x plus 1? Minus 1? Thank you. Plus 1? Plus 1. Sold. And negative 2 minus 1 over 3. Whoops. 1 over 3 times x. Here is the intersection of those two lines, which confirms what we just found. So that's what we're solving for. Take a screenshot, it'll last longer. And there. Crop this up a little bit. Well, nice. And what's this? There. So we did it, found the intersection. And that'll be the procedure, right? If we're finding the intersection of two lines, right? Then set them equal to each other, solve for the x, and then solve for the y, and then you have the intersection. Therefore, the intersection is at -0.9, -1.7. It's good. Okay. So then in section 2.3, which follows here, section 2.3 is an on your own section. Because it's word problems, right, with lines, and so constructing lines from word problems. Constructing lines from word problems. Word problems. That's hard, right? But once you see enough word problems, you start to recognize kind of patterns and, oh, okay, when they say it like that, this is what they mean, right? And so that takes practice. Okay. And I do want to point out, where is it? Where's my Moodle? That I did post, so here, the section 2.3 examples are posted above, and then I've posted the solutions as well. Yeah? And so where I kind of explain how to approach these problems. Okay? And then you've got your separate problems to work through. Okie dokie. Section 2.4 is fitting linear models to data, which is just touching into statistics, which is my jam, right? And so I get carried away in this section a little bit, but it's also one of the more common ways that we use straight lines is fitting linear models to data, right? So you can imagine if I have an XY measurement, right, then I can plot it like so, right? This is what we call a scatter plot, okay? And you've probably seen them before, right? Something that looks like this, and you've got your, and I've got beef with this graph, but this is your x-axis and this is your y-axis, right? And so you've got your x measurements and your y measurements, and together they make coordinates, of course. I have posted, wow, I keep going back to, good thing I've got it pulled up here. Wait, maybe. I did post, shouldn't be hidden, it's later. The section 2.4 regression example. Okay. Regression is just a fancy way of fitting a linear model to data. Okay. And so there's an Excel spreadsheet that I'll pull up as well. So you're welcome to open it, but you don't have to. I'll have it on mine, right, to show you. Okay. Because most of the time we use Excel to do these things, or some other software. Right? We don't want to be plotting by hand. That's crazy. No? So fitting linear models to data is also known as linear regression, which you'll have to wait until you take the data science portion, right, of the program, but that's really just statistics rebranded. One day, all the statisticians woke up and they said, you know what? I think I'm a data scientist because it sounds cooler. And so data science is really just statistics with more report writing. So it is just statistics. Just. My favorite thing, I shouldn't say just. So the Excel sheet that I posted on Moodle should look like, I thought I opened it, but where is it? Here, you recently opened this. Phew. Well, so it looks like this. We've got the data, and then I've made the scatter plot. So what's this example about? The table below shows the number of cricket chirps in 15 seconds and the air temperature in degrees Fahrenheit. Plot this data and determine whether the data appears to be linearly related. Now, we've got our chirps, the number of chirps in 15 seconds. Right? You sit outside, you've got, I don't know, some cricket, and you record the temperature, and then you listen and see how many chirps you get in a 15-second time span. So we get 44 chirps when the temperature was recorded to be 80.5 degrees Fahrenheit. I saw this thing where Fahrenheit, and I don't know, it seemed to make sense. You can think of Fahrenheit as a percentage of hotness. And so 80.5% hot is pretty hot. Whereas 57% of hot is not that hot. I don't know. I don't know. I don't know how Fahrenheit makes sense to anyone. But anyways, seems to. And so that doesn't matter. These are just measurements, right? 2 measurements. So one thing that I will say I have beef with, and did I stick with it or no? I kept it the same, is usually we would put the dependent variable on the y-axis. So the thing that depends on changes in the x variable, where the x variable is often called the independent variable, right? Just kind of moves independently. So my beef is this. Do the number, or does the temperature depend on the cricket chirps? Not really, right? It should be the other way around. And so I would say, well, the cricket chirps probably depends on the temperature, right? So I would have switched these x and y's, but for consistency, we're just going to keep it as is. I don't know why he did this, but I didn't catch it in time, so. And then now I'm just reusing it, I guess. So here, I'll make a note. What color should I do it in? Note. We typically, I'll do it in red because that's how mad I am about it. We typically have the dependent variable which would be the chirps. Right? Chirps depends on the temperature. That seems reasonable, right? But if I say the temperature depends on the chirps, that doesn't seem reasonable anymore, right? And so we typically have the dependent variable, which is the chirps in this case, on the y-axis, and the independent variable which would be the temperature in this case, on the x-axis. But we're just going to move through with what we have. But we will use what is given, even though it pains me. And so you can make a scatter plot in Excel and it'll look similar to what's in the examples as well. And, oh, I don't have a pointer in here. I'll do this. Screenshot, then I'll have a pointer. Bring it in. Uh-oh. Gonna need to bump these down. Whoa. Whoa. Make room. I'm gonna try my best to not go overboard on my favorite topic. It's hard. So in Excel, you can make something like this, where it requires that you have your X variable in the first column and then your Y variable in the second column. So if you wanted to copy paste and switch them up and see what it would look like. Oops, I forgot the chirps down here. I cut it off. This is the chirps. Then this graph is what? It's a zoomed out version of this graph, right? Notice here, we don't go to 0. We don't go to 0, 0, right? That's something to pay attention to. Because it just means that it's a zoomed in section of the graph, right? Which we'll talk about why that's important in just a moment. Okay. So plotting the data looks like this, or you can use Excel to try it out, right? And you can plot it. And so what are we looking for? We're looking for, does this roughly resemble a straight line, right? I say, yeah, I mean, I can kind of look at this and broad strokes. There's no other shape that I have in mind that I could use to model this, right? And so what does that go back to? That goes back to our toolkit functions, right? You could have a quadratic, right? A parabola, right? Things can look like a parabola, which means you would model it with a parabola, right? It could look like a, I don't know, x to the 3, right? That's kind of harder to find, but can happen, right? And so kind of the more common models that we use are either a parabola or a line, right? And so a lot of things can be modeled with a line. In water engineering, especially, sometimes or often what you do is you manipulate your variables until they look like a line, right? And so you can do transformations, take the log of things, right? Which we won't get to for a little bit, right? But logs might sound familiar, right? And so taking the log of a value can turn it into a linear function. But this to me looks like, in general, I can model it with y equals mx plus b, which is what linear regression does, which means that we can find a line of best fit, right? So the line of best fit can be modeled by some y equals mx plus b. Now, what's nice is we can use Excel, and if you right click on a point, right, it'll say add trend line. So it'll look like this. Pull it up. If I, oh, can I right click? I can't. It's letting me draw on it somehow. Not sure how. Oh, draw, home. Oh, it just wants me to draw. Anyways, clearly I did this on a computer and not on my on my laptop, because now, I don't know, it's easier on a computer. Right? You can right click on a dot, and then it'll say add trend line, right? And I think it gives you some options. Notice that here, what's this? y equals 1.1432x plus 30.281. Looks like a line to me. That's the equation of the line of best fit. There's also an r squared, which I'm holding off on just a little bit longer. So here, this is the line of best fit, which is our model, right? Line of best fit, I think makes more sense to a lot of people, right? And I remember in high school, I think it was in chemistry or physics or something, and we had to draw our scatter plot by hand. And then we were told to find the line of best fit, and you just took a ruler and you just did it. It's a little bit, it should be a little bit fancier than that. You should use Excel because there are kind of built background formulas for finding the line of best fit. Right? Minimizing the sum of squares. Okay, that's it. Good. But right, so there are background formulas for finding this thing, and Excel just does it for you. Okay? But doesn't it sound cooler to say model? Here's my model. Wow. What do you use models for? In math and stats, we use models to make predictions, right? You're trying to predict the temperature, or you could work backwards and you could predict the chirps, right, at some temperature. So you can move between the two. So we're told that the line of best fit is y equals 1.1432x plus 30.281, right? Which means our slope is 1.1432 and our intercept is 30.281 because it's not attached to the x. You could rewrite this, right, where y is the temperature and x is the chirps, right? And so you could rewrite it in terms of the variable names, which might be helpful. So, or, oh, I'm really zoomed in here. Wait, don't do that. Or the temperature is equal to 1.1432 times the number of chirps plus 30.281. So models, we use models to predict stuff, like we said, predict stuff, X and Y, right? Backwards, forwards. Usually we use it to try to predict Y, but in our case, we're going to be able to move back and forth. So some caution is required because we could be interpolating or extrapolating, right? I love words. Etymology is kind of the breakdown of words, and it provides a lot of clues, right, for what you're doing. And so inter means between, right? And extra is outside, right? And so interpolation versus extrapolation, right? If you had to guess, knowing inter means between, right? Then maybe not guess yet, but interpolation is when we predict a value inside the domain and range of the data. Okay? So then, okay, knowing that definition, then what do you think extrapolation would be? That's if I use my model to predict outside the domain and the range of my data, right? Which happens a lot. Sometimes we have to, right? Predicting into the future. I don't have data points there. Okay. Or, right? Sometimes things like the intercept, right? The thing about lines is that they keep going forever and ever and ever. Right? Let's see if I can extend this line here. Keeps going and going and going, right? In both directions. I'll extend it all the way. Right? Just keeps going and going and going. That's what's nice about lines, but also that's the trouble with lines, because it means we can use these lines for any value. But we only built it on these data points, right? And so what we're going to say is that our predictions are reliable for X in the domain, right? And we know how to find the domain. Here I've got a graph, right? And we know how to find the domain of this thing, but now the domain is kind of the values of X that are in my data. Okay. And so roughly between, and there's a little bit of wiggle room, right? Roughly between 15 chirps and 45 chirps, I would say my model should be pretty reasonable, right? And so the predictions are reliable between X equals 15-ish, right? It's a little on the outside, but like I said, there's a little bit of wiggle room. And let's say 45 and X equals 45. Oh. Predicting the temperature for any number of chirps outside this range would be considered extrapolation. Okay? And the only problem with extrapolation is that our predictions are unreliable. And we've seen that before, right? The heights of children is steadily increasing, but then we have this knowledge that, okay, well, at some point we stop growing, right? But if you were to extrapolate, right, and keep going with that line, you would get some insane predictions. They're predictions, yeah, but they're unreliable, right? Because you're extrapolating. So that's the reason. And then the same thing goes on the y-axis. So here my y's go somewhere between kind of, let's say 85-ish and 40, or I guess 45 to 85-ish. Right. So temperatures between 45 and 85 they're going to yield relatively good predictions, reliable predictions for the number of chirps, right? If you're working backwards. Right? But anything outside of that would be an extrapolation, right? And so what does that mean? It's all coming together now. What's the interpretation of the y-intercept? That is your y when X is 0, right? And so that's the temperature when the number of chirps is 0, okay? We see from our data that doesn't seem to happen. Crickets are gonna chirp, I guess. And so, right? So here, the y-intercept is an extrapolation. That can happen, right? Just if X isn't reasonably 0. Okay? And so here we see that the y-intercept, this is the y-intercept is an extrapolation. Okay. It's the predicted temperature when the chirps is 0. Okay. So we want to be careful, right? Interpolation, you're working inside your data and you can be fairly confident in your results, right? In your predictions. Extrapolation, it's still the prediction, right? So you can still move ahead and do it, but you should usually make a note that, hey, this was an extrapolation and this is an unreliable prediction. Okay. And I'm trying, let me just make sure. Yeah. I'm trying not to do it all on the one slide. So here, it's not slides, but one page. Would predicting the temperature when crickets are chirping 30 times in 15 seconds be interpolation or extrapolation? And so we're going to make the prediction and discuss if it is reasonable. And what I'll do is I'll bring in a fresh copy of the graph, our graph. And I'm just going to crop this up here. We've got our chirps down here that I should have kept on there. So what do we want to do? We're asked to predict the temperature. Our line of best fit is our prediction for the temperature when X is 30. So from here, X is 30. I go up here and I get my predicted temperature. I see that X is 30 is within that reliable range, right? And so it's an interpolation. And so since X equals 30 is within, I'll say, the domain of the data, right? That's your X values, the domain of the data. It is an interpolation. Well, that's our first thing. We want to make the prediction, right? We've been given the equation of the line. We're so used to building these lines, right? We know how to do that. But here, as long as we know how to read that output, right, we can use the equation replacing the y with the temperature if you'd like, and the x with the number of chirps, and then we can make the prediction. So we want to predict the temperature when the number of chirps is 30. 1.1432 times 30 plus 30.281. The temperature, the predicted temperature, I should say, 1.1432 times 30 plus 30.281. I get 64.577. Careful. You want to multiply these two together first and then add the 30.281. Right? Bed mass. So then the predicted temperature would be 64.577 degrees Fahrenheit. At 30 chirps, I guess, per 15 seconds, we predict the temperature is 64.577 degrees Fahrenheit. And since this is an interpolation, right, this is a reliable prediction. Since this is an interpolation, this is a reliable prediction. It's just a fancy way of getting a line, using the line, kind of understanding some scatter plots. How about the next one? Would predicting the number of chirps crickets will make at 40 degrees Fahrenheit be interpolation or extrapolation? So now we are told that the temperature is going to be 40 degrees, right? But memory serves, we said Well, somewhere between 45 to 85, I would be comfortable with those predictions. And so I expect it to be an extrapolation. No surprise there, right? There's always one of each. If I'm doing it right. Oops. So now, and I'm working the other way. Where the temperature is 40. And I guess we can extend this here to just over 30. Right, the line continues. And we want to make a prediction. But it's outside. Right. In this range is an interpolation, which makes this an extrapolation, right? It's outside the range of our data. And I'll make a new page. I'll say since, and I feel like since temperature of 40 degrees Fahrenheit is outside the range of our data, this would be an extrapolation. Is outside the range of our data. This would be an extrapolation. Oh. We can still make the prediction, right? But with a little red flag saying, it's an unreliable prediction, but it's the best thing I have, right? It's my best guess, right? And so we can go ahead and still use the same equation. What you could do is you could refit it with the chirps on the y and the temperature on the x, but that seems excessive because we can just solve for the chirps, right? We're told that the temperature is 40 and I want to find the number of chirps. Solving for the chirps, which you can denote by X or C or whatever you'd like. Right? Chirps. 40 minus 30.281. I get 9.719 is 1.1432 times the chirps. Dividing both sides by 1.1432, I get the chirps must be 8.5015745528. I know I can't stop. Can't stop, won't stop. That's our predicted number of chirps, roughly 8.5. So make the prediction and discuss if it is reasonable. Now it is an extrapolation. Right? Do I still feel comfortable with what's happening here? Maybe they just didn't reach 40 degrees Fahrenheit. Right? It seems reasonable that it would keep decreasing, right? But I'm going to hinge it on it being an extrapolation, right? In these scenarios, discuss if it's reasonable, right? You can sell me either way, right? As long as you mention that it's an extrapolation and so it's unreliable, right? But then you could follow it up and say, but it seems reasonable, right? That a downward trend would apply or something like that. So what did I say for the last one? Yeah. so therefore, at 40 degrees Fahrenheit, we predict approximately 8.5 chirps per 15 seconds. That's a fact. Right? But then I'm going to say, since this is an extrapolation, right, then this prediction is unreliable, and I'm going to leave it there. And that's all I'm expecting of you. Since this is an extrapolation. Listen to me sound it out there. Since this, it's worse, is an extrapolation, it is an unreliable prediction. That's all I need you to take away from this exercise, right? Interpolation, you can trust it, it's reliable, right? Seems reasonable. Extrapolation, unreliable, right? Proceed with caution. The problem is usually it's our only prediction that we have available. And I have so many examples of extrapolation being published in even reputable newspapers and things like that. So something to look out for now that you know. All right. The word correlation, you've probably heard before, right? Correlation. Oh, is there a correlation between those two? We've even seen the spurious correlation website, right, where things are moving together, right? They're correlated, right? Two things being correlated means that they have the same, they follow the same patterns, right? So in statistics, right, and in linear regression, we use the correlation coefficient. We denote the correlation coefficient by a lowercase r. Right? C was already taken, of course, and so they went for r. I shouldn't say of course, it was. But there's two r's in there, so I guess it makes sense. So the correlation coefficient, there's other reasons, but not for us. We denote it by a lowercase r. And r is between -1 and 1. A positive r means that you have a positive relationship, which means you have a positive slope. Right? So here, hello. Redo, there. I never get to redo stuff, I always have to undo stuff, right? And so here the slope is positive. If you have a positive correlation, it means that they're moving together in a positive direction. If you have a negative correlation, it means that the slope is negative. In fact, the correlation factors into how we calculate the slope in the background. But that's for your data science course. The closer the value is to 0, the more scattered the data is. And then the closer the value is to 1 or -1, the less scattered the data is. In fact, a correlation of 1 means they're perfectly on the exact same line. And so I like to do this kind of, I don't know, number line, I guess. So the correlation as a fact goes between -1 and 1. So we're restricted between these two values. Put 0 in the middle. Fair enough. Now, an example of a graph with a correlation of 0 looks like this. Just a random scatter, no correlation. right? I think if you looked at that and you were prompted to use the word correlation, you might kind of nudge yourself in that direction. No correlation, and you'd be right. Right? And so what does a perfectly negative relationship look like? That's going to look like this. 1, 2, 3, 4, 5 points. Let's do that. Right? They're perfectly on the same line in a negative direction. And then, of course, same thing on the positive correlation side. They're perfectly on the same line. Of course, this is a scale, right? And so we said here I've got these positive relationships, and a negative correlation we said is a negative relationship. If we go to our graph, right? Our graph looks like this. And maybe I'll use the original one, this one, because it doesn't have all the information on it. I know. Cheeky. Looks like a positive relationship, right? And it's quite strong, right? And so I would say, and this is kind of going beyond here, but this is somewhere between 0 and 1. It's going to be very close to 1 just because it looks so strong, right? And so, right, it's positive because I have a there was some flickering going on. Hello? Okay, it's still recording, not just. I don't know. There. So. Okay, fine. As a general rule, around, so between 0.5 and negative 0.5, it's not going to look like any sort of pattern. Once you hit 0.5 in either direction is when you start to see some pattern, right? Just being able to convince yourself that, oh, there is a pattern here, right? Otherwise, it just looks like a cloud most of the time, right? No correlation. And so here you start to see a pattern kind of once you reach 0.5. So it's going to be quite high because we really see a pattern. Right? So in the Excel output, should have just gone to the screenshot. I've calculated the correlation for us. There's a correlation function in Excel. And so if I click here, you can use the equals correlation of your X variable and your Y variable. And then it calculates it for you. You don't need to be able to do that, but the correlation is 0.950923338. So from the Excel output, from Excel, we see that the correlation, which is your R, right, was, let me snag it here. .950923338, right? Which is close to 1, right? 0.95, pretty high. Right? It's positive, which tells me I have a positive relationship, which checks out. right? And so you can use Excel to calculate the correlation, right? But it really just tells us how tight our points are around the line, or if there's a lot of scatter, right? If your points are tight around the line, so then you have a high correlation, right? Do you think your predictions are more or less reliable? Even more reliable, right? If you're interpolating with a high correlation, right, that's a really reliable estimate. You're expecting these points to behave just like this line, right, or close to it, right? Whereas if you have a low correlation, then you've got slightly less reliable results. You know? And so a high correlation means I should say our predictions are more reliable than if the correlation is low. Right? If it's close to 0, you expect this kind of scattered behavior, which kind of intuitively means that you have these less reliable predictions. Now, on your output,
Question.
yes, hit me.
If the correlation is 1, is still the extra
And you're extrapolating,
is only
It-
line,
it would still be unreliable.
all the extra ones are unreliable.
Yeah, all extrapolations are unreliable. And any low correlation is also unreliable. But it's kind of the extrapolation trumps the correlation, if that makes sense, right? If you're extrapolating, it's unreliable. And then if the correlation is low, you kind of have to use your judgment. Right? Depends on what the data is too, right? If you have some background knowledge about how this thing behaves, that's helpful.
If data looks feeling like similar,
Yeah,
that means we cannot really say the extrapolation is only line. Because the data only shows this much.
yeah. So it depends on, for example, if you're doing water measurements and you just only measured in the summer, right? Then you could say, okay, in these summer temperatures, for example, if the temperature is one of the things that you're measuring, and then some, I don't know, dissolved oxygen or whatever. Right? And so, because that's the only water thing that I know. I'm learning more as I go, but dissolved oxygen, I know that's a thing. I know that's a thing that you guys measure. So, right, so if you're working in the summer months, and then you have some background knowledge about how it would behave and should behave in the winter months, right, colder temperatures, then you are allowed to use that. But that's often a luxury that just a plain old statistician doesn't have, right? I don't know how this thing behaves. So sometimes background knowledge is also important. Right? I don't know how crickets behave. Do they just stop chirping at some temperature? I don't know that, right? And so that has to factor in as well. Yeah. So another common statistic that we report is called the R squared. It's the coefficient of determination, but don't worry about that. So another statistic we often report is R squared. I'll bump this down a little bit. In fact, on your Excel output, That's the second part of the output, right? I give you the line and I give you the r squared. Okay? And so most commonly, right, when you're talking to Sydney in chemistry or anyone, if you have to take a physics course or anything like that, right, then you do a lot of regressions and you'll focus on your r squared. So what's your r squared? Even though it's a capital R, it is just your correlation squared. It just kind of grows up when you square it, which is kind of funny, right? And so the r squared, oops, I combined it. The r squared is the correlation squared. Okay. What does squaring a number do? Makes negatives positive, right? And if I go back to my number line here, right? If it's between 0 and 1, and I square any value between 0 and -1, or -1 and 0, I should say, right? It just kind of folds onto itself, right? So now r squared is between 0 and 1. That's ripe for a percentage, right? And so the technical definition of r squared, and you don't have to remember this, but I can't help it, is the percentage of variability in your y that's explained by the least squares regression line on x, which feels very similar to the correlation, right? Similar, but not the same. Because we had a correlation of 0.95, right? And if you take this whole thing and you square it, you should get 0.9043. Right? Decimals are funny when you square them, they get smaller. Right? And so, right, so in our case, r squared is roughly 0.950, it's right here, 9509238 squared. Let's try it. 0.9509238 squared. Phew. I get an r squared of 0.904255276-ish. Right? And so r squared is a value between 0 and 1. And 1 often reported as a percentage, right? Because it's between 0 and 1, and so it's kind of ripe for a percentage, and it is a percentage. Often reported as a percentage. I should write that out. Sloppy. Percentage. But similar to the correlation, right? A high r squared means that you have reliable estimates, right? And so again, a high r squared value means that you have reliable estimates. Means I should say predictions. Estimates and predictions are the same, but I've been saying predictions. Means your predictions are reliable. As long as you are interpolating. Right? As long as, I'll add that, you are interpolating. So most of the time, right, in physics, chemistry, whatever, you'll just get the equation of the line and the r squared, right? And then a high r squared, you're happy, right? And so a lot of the time you'll talk about the R squared. An R squared of 0.9043 is high. Yeah. And it's tough because there's not really a guideline. I would say an R squared 0.6 is still really good, right? What's the, if the R squared is 0.6, what's the correlation? Top notch. I'll do a little example. If R squared is 0.6, what is the correlation? You guys are too clever. I'm trying to set you up. If R squared is equal to the correlation squared, depending on the textbook, sometimes they use a little r just to be consistent and to show that it is the correlation squared, right? And so if the R squared is 0.6, and I want to solve for the correlation, which is your lowercase r, then I can take the square root of both sides, square root of 0.6, but as I already heard murmurs, you want to be careful because you're plus minus, right? Your correlation goes between -1 and 1. How are you going to know which one it is? It can only be one of those, right? Depends on your relationship. If you know your slope, right? If it's positive, it should be the positive value. If you know if it's negative, then it's negative, right? Or if you have the graph, you can look at the relationship, right? And so here, to pick the appropriate sign, right? Consider the slope, right? If it's positive, negative, negative. Consider the slope or look at the graph if you have it. If we consider the positive, right? Say m is greater than 0, right? The slope is positive, then the correlation would be the square root of 0.6, which is 0.7745966692, which is quite high. Anything past 0.5, you'll start to see a pattern. 0.5 and 1, right? Starting to get strong. And so 0.77, halfway between that. So it's pretty strong. Okay. So I would say 0.6 is a nice kind of, it's not a hard cutoff. Depends on what you're measuring, right? If what you're measuring is inherently variable, right? There's a lot of variation, then you would be happy with a lower R squared, right? I've seen reports where they're happy with an R squared of 0.2. Hello? Because there's so much variation. Right? Okay. Sometimes we get output like this. And if you're comfortable working with a graphing calculator, the output would look something like this. And so we don't have that, but I'm pretty sure there is a way to enter data into here and have it give you regression output. I just haven't explored it, but I'm pretty sure. Is now the time to explore it? Not really. But there is a spreadsheet option, and so I feel like that would be the way to go. But anyhoodle, one can play around with it. But on the test, right, I'm not expecting you to have Excel or anything like that. So I would give you output. right? I would give you output like we saw here, right? I could give you this graph, right? Ask you if it's an interpolation and extrapolation, what's the equation of the line, right? What's your R squared, what's your correlation? Lots of questions I could ask just by giving you this output, right? And so you don't have to have software to do it, right? But you need to be able to read this and grab information. Another way that I could give it to you is a summary like this. And so a regression was run to determine if there is a relationship between the diameter of a tree, X, which is in inches, and the tree's age, Y, in years. We understand how trees work, and so there should be some sort of relationship, probably. We'll find out. The results of the regression are given below. Use this to predict the age of a tree with a diameter of 10 inches. Okay. We're told that X is the diameter and the ages are Y. Okay. And then we're given this kind of cryptic output, but it actually does tell us everything that we need. Okay. First, it tells us the format of the line, right? A is our slope and B is our y-intercept. Okay. And then it tells us, hey, A is 6.301, right? Our B is negative 1.044. Our R squared is 0.94, and our R, our correlation, is 0.97. Right? Even if I only give you, there, can I zoom in? The R squared and the R, from there, you can tell me if it's a positive relationship or a negative relationship, right? Because R squared went to a positive correlation, and so right away, right, I know that it's a positive relationship. So I'm expecting my slope to be positive. Now my slope is A and it's positive. Nice. All right. So lots of information here as well. What I'm going to do is first summarize here. So we're given that X is the diameter and Y is the age in years. We can kind of grab what we need from this output, right? And so we can start by constructing the line y equals ax plus b. Let's replace those with some question-specific variables, right? Just because it makes it nicer to look at. So y is the age, and a is 6.301 times the diameter. And you can use A and D if you want, but it might get confusing. Plus negative 1.044. So I'm going to just make that a minus right away, 1.04. So I've snagged this information just from here, and I've put this all together and put this all together here. Well, a little bit easier to look at, I think. We're asked to use this to predict the age of a tree with a diameter of 10 inches. Now, what's tricky is I don't know if this is an interpolation or an extrapolation because I don't have the graph, right? So then my next best gauge of how reliable it is going to be my correlation or my R squared, right? Because they're definitely related. And so if the diameter is 10, we can find that the age of this tree, 6.301 times 10, let me, in inches, 10 inches. You always want to make sure that I try not to mix up the units. That'd be rude. That's for your other courses, unit conversions. All right. But you're probably getting pretty good at it by now. And your calculator does do some unit conversions. Right? Do you guys use your calculator function for it? Or do you have that little ruler? Little ruler? It's cute. But there's this, I have a conv function. Might be fun. Let's check it out. Length, area, volume, mass. Whoa, 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 whoa. There's a lot, actually. Mass, velocity, pressure, energy, power, temperature. Holy smokes. Think of all the things you can do. Wow. Play around with your calculator. Huh? Might be nice. Won't need that little ruler. Maybe anymore. I found out last term that so we were talking about units. Steve and I talk about the wildest stuff. Not wild, very, very tame. So we were talking about a hectare, right? So a hectare is a measurement. And so we're like, hectare, that must mean that there's an air, an aura, I guess. And there is. So interesting. Never heard of it. An air aura. I have to look up how to say it. Anyhoodle, the predicted age when the diameter is 10 must be 6.301 times 10 minus 1.044. So the age, 61.966 years old. No? I'll do a follow-up, right? Is this a reliable prediction? Without the graph, we don't know if this is an interpolation or an extrapolation. And so I'll write that down. Without the graph slash data, right? If you had the data set, you could create the graph and you could look at it, right? And so without the graph or the data, right, we don't know if this is an interpolation or an extrapolation. That's a fact. But we are given that our R squared and our correlation is really high, right? So since our R squared and correlation are high, right, then we expect this to be a reliable prediction. I want to start the sentence with but. Are we allowed to do that yet? Start a sentence with but? Probably not. It's like one of those rules that we had drilled into us. Never start a sentence with but. Because. I think you can't start it with because either. Can you?
If you put a comma, I think you can.
Therefore. Yeah, can you?
You could do like, because this is this, you could put a comma and then continue on the sentence.
How about but? I think no. It sounds bad too. I think you don't start it. However, there we go. The age-old workaround. However, since our R squared and R, now they've used a lowercase r squared, right? So just link those two up and you're welcome to write a lowercase r squared. I'll know what you mean, right? I'm just an old dog learning new tricks, I guess. So I'm hooked on the capital R squared. And so since our R squared and R are high, right, which I mean close to 1, oops, I expect this prediction to be reliable. I expect this prediction to be reliable. Kind of the hierarchy of reliability. Nice. Oh, so a couple of different ways that I could give you some output and have you gather some information. But I think the graph is probably the easiest way with the output. And I think that's okay. How am I doing? And I don't trust that. 11:29. Any questions before we get into our last section in chapter 2? Very exciting. All right. Yeah.
So I have a question. How does correlation work when we have like tree values that we expecting? Because for example, the tree graph
Mm-hmm.
not be accurate because trees grow differently based on their elevation. You know, how would you shoehorn like elevation data set into that?
So there is a way to do it, but you wouldn't be able to use the correlation anymore. So a correlation only works for 2 variables, right? X and Y. Now you can make a regression incorporating more than one variable of X, but it would be called a multiple regression analysis, which again, you have to wait for your data science course to see it. But then you'll have multiple variables of X, things like the diameter, the elevation, right? Maybe some other things, right? And so it is possible, and it will be related because you'll get an adjusted R squared. And so it'll behave the same way, but that adjusted R squared, you get penalized for adding too many things in, right? And so then it kind of makes an adjustment. But the R squared, your kind of how you use it stays the same. So it is possible, but you move away from the correlation because it's just restricted to 2 variables. Nice. Nice. And yeah, I can talk about stats for a very, very, very long time. So any other questions before we'll start 2.5, kind of get a jump on it, and then we'll continue it on Thursday, of course. 2.5 is on your test. I know, right? And so usually what happens is we'll see how far we get today, but I don't anticipate too far. So then I like to test it kind of lightly on test 1 and then a little bit harder on the final exam. Okay, because then you'll have time to kind of work through it. Okay, absolute values, right? We know from our toolkit functions what this graph looks like. Looks like a V. Right? Just generically, we have something that looks like this. This is the absolute value of X. What does that mean? Well, it's really just a piecewise function, right? For us, probably seen the absolute value function before, right? And to us, it just says drop the negative, right? But how does it drop the negative? Right? So if f of x is the absolute value of x, which we use these vertical bars right around it, then it becomes a piecewise function. It's going to be just x if x is greater than or equal to 0, right? If it's positive, you just leave it as positive. Right? But it's going to be negative x if x is less than 0. A negative of a negative makes a positive, right? And so that's really how we drop the negative, right? You take the negative of a negative, it makes it positive. So we know what to do here, but we just probably haven't thought of it as, and I should use 2 different colors, I realized. Actually, let's use pink for this one and green for this one. So if y equals x, what does that line look like? And I'll do this instead. Looks like this, right? Just a diagonal line. x equals y equals x, right? 1, 1, 2, 2, 3, 3, blah, 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 right? Same thing for our negative x. What does that look like? We have a negative slope, right? Slope of 1, technically. And so we get this downward diagonal. I'll make it, or kind of like this, where y is negative x. And together, right, they meet up and they make the absolute value function. Right? And so, or do this. Together, they make, oh, hey, come on. Absolute value of x. So it's just a piecewise function. And so if we see an absolute value function, which is really easy to recognize, right? Because we've got those vertical bars, then we know where to start. Right? So a default absolute value function, oops, actually cleaned it up quite nicely, but should be sharper. These there. Ish. Our default, right? Just a v at the origin, 0, 0, right? But what can we do? We can transform it, right? We can shift it to the right, shift it to the left. We can squeeze it, which I can't remember if that's shrinking or or what. We can flatten it, right? Can flip it upside down, right? We can do all these things, right? And so just as an exercise, because I don't want to do it next day, what if you have to write an equation for the following graph? You can break it down step by step. So where you're starting is at this absolute value of x function. Yeah? And then we're going to manipulate it, right, as we go. So here, step 1 is to start with y equals the absolute value of x. Okay. First thing that I notice here is compared to my default absolute value function, right? This has been flipped down. And on your formula sheet, right, you can see that that means that I have to throw a negative out front, right? Negative y, which is going to look like this. And so step 2, it's been flipped, flip on the, so here, this is going to get flipped down on the x-axis, right? Which is going to look like y equals negative absolute value of x. Okay. And we can check in, where's my Desmos? Where is it? Here. If it behaves. Okay. The absolute value of x, I don't have a shortcut here, but if you go into your functions, it just might have some functions here. Was it in the... No, sorry. It's right there. Just tiny. No, it's the same size button as all the others. Just missed it. The absolute value of x, close that bracket. We start there. Okay. What if we do negative absolute value of x? Okay, good. So far, so good. Right. That doesn't exactly look like this, though. Right. Let's tackle the slope. Right. Absolute value of x has a slope of 1. Right. Even negative 1 times the absolute value of x, right? But here I suspect that this doesn't really look like a slope of 1 anymore, right? And so how can we pick that apart? Well, if we just focus on one of these slopes, right? They should have the same slope. One's just negative and one's positive, right? And so if I have a rise of 2 and a run of 4, right? I have a slope of rise over run 2 over 4 or 1/2, right? So here, step 3, probably the hardest step. Find the new slope. Okay. So we find rise over run. Since we have the graph, I think that's the easiest way to do it, but you've got other tools for finding the slope, right? If you've got points on there or something like that. So we have a slope of 2 over 4 or 1/2. Where does that go? In our y equals mx plus b, right? Then I've got this negative, and I'm just going to sneak it in here, right? Negative 1/2 times the absolute value of x. So then I'm at y equals negative 1/2 times the absolute value of x. I'm going to try it in Desmos and see how it looks. How she looks. Negative 1 over 2. Step that out times the absolute value of x. Okay, looks okay. Kind of needed it to be a little bit flatter, right? Which it is. The green one is flatter than the blue one. And so I'll wait to confirm, but I'm feeling pretty good. So now what do I need to do? Now we're on Easy Street. All right, gotta da-da-da-da-da and da-da-da-da. I know, I should close caption that. Da-da-da-da to the right and da-da-da up. All right, so now step 4. We can shift it. First, I'm going to shift it from 0, 0 over by 1 unit, right? To the right by 1 unit, right? How do we do that? I have to manipulate my x in here, right? X minus 1. For me, that's counterintuitive, right? But that's how we move to the right. Okay? And so here, move to the right 1 unit, putting me at y equals negative 1/2 times x minus 1. Then I'll try to squeeze it in here. I'll do them out in the same go here. Step 5 would be move up 2 units, right? Move up from 1, 0 to 1, 2. Okay. So move up 2 units. So the final graph would look like negative 1/2 times the absolute value of x minus 1, and then up 2 units. So then I can add to y. Let's see here. Where did it go? I'll do the negative 1/2 times the absolute value of x. Oops, minus 1. Okay, good. Shift it over just like we wanted it to. Whenever I zoom in, it doesn't want to work anymore. But let's try that. Oops, I'll need there. And then in my final step, negative 1/2 times the absolute value of x minus 1. Do all the things, plus 2. Ah, right. And from here, you can confirm that it looks the same as what we were given. Right? So just going through incrementally and manipulating things, right? I'll bring this in. We put a lot of work into it, so may as well. Where can I squeeze it in? Fresh page. Wow, luxurious. No. Doesn't know how to find stuff. Mm. So here, right, you can confirm that it looks the same. And it does. Okay. Can I just show you how to solve these? Come on. If you have to solve an absolute value function, right? You want to go back to what the absolute value function says, right? If f of x is the absolute value of x, then we get x if x is positive or negative x. So x is greater than or equal to 0, and if x is less than 0. Which means that inside your brackets, right, you have two options, right? 2x minus 3 is either positive, right, and it has to equal 8, or 2x minus 3 is negative, and it has to equal 8, right? Or I think the easier way to do it, bless you, is you could say, well, it has to be negative 8, right? That's probably the easier way to do it. Yeah. Thinking about 2x minus 3, the absolute value of 2x minus 3, so I've done some shrinking or expanding, can't remember, on the x, right? And minus 3, shifted it over, right? So we can graph this.
I noticed that it has the 2x inside of the absolute like brackets.
Yes.
Whereas when you put them outside.
I wonder what the different behaviors would be, actually. Because we got there with it on the outside. I think it should behave the same either way. Because the absolute value... I'll have to play around with that, actually. I noticed that too. So here the 2 is on the inside of the absolute value. Versus, so 2x minus 3, absolute value.
You would find the absolute value of whatever is in the bracket first, then we multiply it by the outside. So that's-
Versus 2 times x minus 3. So there is a difference. Right, because it wouldn't. What if it was 3/2 in here? Oops. Then they're the same. If I expand that too. So you can move in and out as long as you're expanding properly. Like I forgot to. Think. Left with just this one. Nice. Now we wanted it to be at y equals 8. Okay. So what that looks like here, right? Technically what we're finding are the intersections, right? Where does this absolute value function equal 8, right? So for absolute values, we're going to find two solutions, right? One for the negative side and one for the positive side, right? Notice that they're both positive 8, right? So they're still positive for the y's, but we get kind of the negative version and the positive version. And so I'm going to bring this in so we can see it, because that'll give us a heads up for next day when we actually move through and solve this. But you've got the solutions here, and I encourage you to try it, but we'll pick up here on Thursday, so I don't go over time again. If you have any questions, let me know. Otherwise, I'll see you then.
One question for the midterm.
You got it.
What do you recommend as like a study guide for that?
I draw a lot from the notes and the assignment questions, right? And so if you're able to do the assignment questions, right, then I would say that that's a good tool. So I've also posted those chapter, what did I call them? Practice problems, right? And so those would be for extra practice for chapter 1, and I'll post one for chapter 2 as well.
Did you say you were gonna post a practice test?
I'll post a practice test, yeah. Yeah. And so I'm pretty sure I only have one version. So what I would recommend with the practice test is you study until you feel prepared, and then try it, and then you'll have the solutions as well. So then you can kind of check yourself, right? It's tempting to do the practice test and then learn from that, but it'll give you a better idea.
Something other than PowerPoint that will happen.
Oh, yeah.
Yeah, so here, I'll just stop this recording here.